Okay, welcome back everybody to our last video on cardinal. So for arithmetic, we saw that we get a pretty trivial result that addition and multiplication of cardinals always gives you the maximal on the two. Exponentiation, we get some trivialities sometimes, but it's a bit more tricky in general. So this is what we can say. So this part behaves somewhat easily. And it says the following, we claim the following, that if you take 2 to the kappa, or lambda to the kappa for a lambda less than kappa, or kappa to the kappa, or 2 to the kappa to the kappa, you always get the same thing. And you get a cardinal that is strictly larger than kappa. Why is that? Well, the strictly larger we know, because we know that 2 to the kappa, which is the same as the power set of kappa, has to be strictly larger than kappa, right? We proved that the power set is always larger than the set. So the larger we know. Why is that these two are, all of these are equal? Well, we know 2 to the kappa must be less than or equal to lambda to the kappa, I guess assuming lambda is at least 2. And then lambda is less than kappa, so that has to be less than kappa to the kappa. And of course, that's less than, kappa is less than or equal to the kappa, so that's less than or equal to the kappa times kappa. And now, by the properties of exponentiation, we get that this is the same thing as 2 to the kappa times kappa. Those were important properties of exponentiation. And then kappa times kappa, by our previous result from the previous video, that's the same as 2 to the kappa. And that closes the circle, less than or equal at 2 to the kappa. So all of these guys, by the Schroeder-Bernstein theorem, they must be all equinumerous to each other. Okay, so that's quite simple cardinality in that case. There are situations where you, of course, if the base of the exponentiation was larger than 2 to the kappa, you will get a larger cardinal than all these guys. So whenever you take something larger here, you will get something even larger. So this equality only works from 2 all the way to the kappa, but doesn't work beyond. So I mentioned before the continuum hypothesis. Now we can formalize it better. So the continuum hypothesis was postulated by Cantor more than 100 years ago, 130 years ago or something. And it says that every uncountable subset of the reals must be equinumerous to R. So in other words, it says that if you take a subset of the reals, it must be either finite, countable infinite, those are the possible countable sets, or equinumerous to R. So maybe let's write that down. In terms of cardinality, we are saying that if lambda is a cardinality that is less than or equal to the cardinality of the reals, 2 to the aleph naught is how we denote the cardinality of the reals. Remember, aleph naught is the cardinality of omega, of the countable things. 2 to the aleph naught is the one for the reals. Then we have three possibilities. Lambda is finite, or lambda is infinite and countable. Lambda is aleph naught, is the cardinality of the natural numbers, or lambda is the same as 2 to the aleph naught, right? This is the cardinality of omega, this is the cardinality of the reals, right? So it's saying essentially there is nothing, no cardinality in between that of the natural numbers and that of the reals. Every subset in between will have to be equinumerous to one of the two, but there cannot be a size in between, okay? That's what it states, this hypothesis. And it's a very simple statement, right? So it feels like if somebody conjectured this 130 years ago, it should have been resolved by now. Well, it's been somewhat resolved. So this is what happened. In the middle of the century, Gödel showed that the continuum hypothesis, so CH is the continuum hypothesis, cannot be refuted in ZFC. So that means ZFC, so the axioms that we are seeing in this course, Samira-Frankl, cannot show that CH is false. They cannot prove the continuum hypothesis is false, right? So it doesn't. You cannot prove it's false. Gödel showed that by building essentially a model of CFC where CH holds. In the 60s came Cohen, and this got him the Fields Medal. He showed that CH cannot be proved to be true either in CFC. So essentially he built another model of CFC where CH is not true. And this is, by the way, assuming CFC is consistent. I don't want to get into those details. See, the consistency of CFC doesn't follow from ZFC, so these proofs are not in ZFC. They are assuming something more. Of course, nobody doubts CFC is consistent, so. But yeah, just mention that it's beyond CFC, these proofs. Okay, so Gödel proved that he cannot prove it to be false. CH cannot be proved to be false. Cohen proved it cannot be proved to be true. So somewhat this says that at least if you're only doing work in ZFC, the continuum hypothesis has no answer. You cannot prove it true, you cannot prove it false. There's nothing to do. There's a lot of work still on this because you still believe, well, it has to be either true or false. CFC is some set of axioms, but who's telling you that this is all the axioms? Maybe there are other natural axioms that we haven't found yet. Or maybe some other way of thinking about this that will kind of argue that CH should be true or should be false. So there is a work in set theory trying to analyze that. But for now, CFC is still the more solid basic axiomatization for math. And with that, you cannot prove or refute CH. You say, well, that means that we can add CH to the axioms, or the negation of CH to the axiom. Well, this theorem tells you that if you add CH to the axioms, or you allow the negation of CH to the axioms, you stay consistent. It's fine. Either way is fine, because you won't get a contradiction, because neither of them is contradictory with CFC. But how you decide which one you add? Because is it obvious that there is no set in between the natural number, size in between the natural numbers and the reals? I don't see why that would be the case. Or is it obvious that there is one? Well, we definitely don't know any, and you cannot even prove there is any in ZFC. So most likely, well, I don't know. So you couldn't add, like, there is no reason to add or CH or the negation, because you don't know which one to add. There are many theorems that people prove and publish, which are of the form, if you assume CH, blah blah blah, or if you assume the rejection of CH, blah blah blah. So you can work one side or the other, but which one is true, we don't know. Then there's another hypothesis that I should mention, which is the generalized continuum hypothesis. Generalized continuum hypothesis says it's more general, because this is only for essentially 2 to the aleph naught, and it says that if you are between aleph naught and 2 to the aleph naught, then, well, you have to be either one of the two. The generalized continuum hypothesis tells you that for every infinite cardinal kappa, not just aleph naught, for every infinite cardinal kappa, 2 to the kappa is the smallest cardinal larger than kappa. So there is nothing in between kappa and 2 to the kappa. That's what the generalized continuum. So all the way, for all the cardinals, 2 to the kappa is kind of the next cardinal up after kappa. Again, this is a generalization of this one, right? This is for the case kappa equals aleph naught. And the same story works. Actually, when Gödel and Cohen proved these results, they both work for the generalized continuum hypothesis. So it still cannot be proved or refuted, and actually very free. You can let 2 to the kappa be whatever you want. In these models that Cohen builds, even 2 to the aleph naught, like this size of the reals, I don't know, there can be like infinitely many cardinals in between the naturals and the reals, and that will still be consistent. So yeah, there's not much to say about this. Could be true or not. See you guys next week.